Hi everybody. So this is the first video on a totally new topic, which is quantum physics. We've got about 4 weeks of the course left, not including the last 2 weeks, which are going to be presentations and exam week. So we're going to do 2 weeks on quantum physics and then 2 weeks on particle physics, and probably have one online quiz and one worksheet for each of those topics. So in this week's lectures, I'm really going to focus on the meaning of this word quantum here. So if you say that something is quantum or quantized, it means that it comes in a discrete unit, a discrete quantity. So for example, what we're going to focus on in this video is quantization of energy. So classically, energy is thought of being a continuum, right? You can take, say, a joule of energy and you can divide that into half a joule, and you can divide that into a quarter of a joule, and you could keep going on, people thought, forever. So there was no limit to how small quantities of energy you could get. But it was discovered that in some systems, that is not the case. So in some systems, the energy the system can have comes in a fixed unit. There are only certain values of energy the system can have, and values of energy between these two units are impossible. Okay, and this is where the term quantum comes from. Though, as we'll see in the next couple of weeks, quantum physics is actually much more revolutionary than just this idea that energy comes in fixed units for certain systems. It says much more fundamental and profound things about the universe we live in. And hopefully by the end of this 2 weeks, you will have some understanding of what those things are. So obviously, as this is a quick introduction, I'm not going to go into the mathematical theory of quantum physics really at all. But I want rather to explain some of the most important concepts and some of the most important differences between classical and quantum physics. Okay, so I want to start with this slide, which is basically a bit of motivation. By the end of the 19th century, a lot of physicists thought that their work was kind of getting done. So they had Newton's laws, which very well explained mechanics of particle and wave systems, and they had the laws of gravity, and then Maxwell had just come up with his description of electromagnetism, which was very successful. And it looked like there weren't too many more pieces to fill into the puzzle. So here we have a quote from a physicist at the time, around 1875. In this field, he's talking about physics, almost everything is already discovered, and all that remains is to fill in a few holes. Okay, so that's clearly showing that, at least in this professor's opinion, physics is mostly finished in 1875. Okay, and also Max Planck, who is one of the founders of quantum mechanics, when he was a student, he was also advised not to go into studying physics because there wasn't much to do in physics anymore, according to the advice he got. So luckily he ignored that advice and went on to become a very famous physicist who revolutionized physics with his work on quantum mechanics. Okay, so this was by no means all scientists who thought like this at the end of the 19th century. So in particular here, there's a lecture by Lord Kelvin, which was given in 1900, titled 19th Century Clouds Over the Dynamical Theory of Heat and Light. Okay, so these clouds here are two problems which the classical theories could not answer. And these were experimental observations which had no explanation. So the first of these is the Michelson-Morley experiment, which we've seen in detail in the topic of special relativity, and the second of these is the theoretical prediction of black-body radiation, which is what I want to focus on now. And this lecture by Lord Kelvin was very prophetic, looking back on it, because both of these experimental results turned out to require completely new theories of physics to explain them. The Michelson-Morley experiment, as we've seen, required the discovery of special relativity, in order to have a good explanation, and this result on blackbody radiation actually requires quantum mechanics to understand. And this was partially Planck's contribution actually to explain the blackbody radiation spectrum. Okay, so this is blackbody radiation. I'm going to start about talking what it is. So it's light which is emitted by bodies when they are hot. So if you take a certain kind of body, which is known as a blackbody, this just says something general about the material it's made of. If you heat it up, then it will start to glow, right? And at low temperatures, let's say like 900 Kelvin here, as in these cooking elements here, it will start to glow a very sort of dim red color. And as you increase the temperatures up to about 2000 Kelvin, it will start to go more sort of orangey yellow color. And then if you go up to something like 6000 Kelvin, which is the surface temperature of our sun, then it will appear, to the human eye at least, to be nearly white light. Okay. So these light bulbs, by the way, I think you are just old enough to remember these. Modern light bulbs do not work by heating something up until it glows. But there were, at least in the 1990s, and for a long time before that, these things which were called incandescent. I think that's how you spell it. Incandescent light bulbs. And then these light bulbs had, inside the light bulb, they had a little wire like this. And they passed electricity through this wire until it got very hot and started to glow. And that was how the light bulb worked. Okay. So these light bulbs are good approximation to blackbody radiation spectrums. Modern light bulbs are not, because there are various different kinds, but they tend to rely upon emitting light of a certain few frequencies only. Okay. Anyway, so what you do is you take the light from these glowing bodies and you split it into the different frequencies of light. Okay, so they all emit light at different frequencies, and if you use something like a prism, you can split the light into those different frequencies and measure how much light you have at each frequency. And if you do that, you end up with some graphs that look like this. Okay, so here on the x-axis, the frequency, the different frequencies of the light are plotted. So you probably can't see the scale. This goes from 2, 4, 6, 8, 10 times 10 to the 14 hertz. Okay, so the bit we can see is somewhere in between about 4 and about 7 on here. That's the visible part we can see. Okay, and on the y-axis, it's plotted energy density. So how much energy, what's the intensity of the light at these different frequencies. Okay, so what you can see, each graph has the same scale on the x-axis. The units on the y-axis are not important. You can see that as the temperature increases, the curve is stretched more towards higher frequencies. Okay, so for the heating element here, there is actually very little visible light. Most of the light energy is here, which is actually infrared, and only a tiny amount of light in the visible part of the spectrum is emitted. For these light bulbs, it's the same as well. The visible spectrum starts somewhere here, so the light we can see is just that much. And this is one of the reasons why these light bulbs are actually not very good, because all of this energy here, which is the vast majority of the energy they emit, is in the form of infrared radiation, which we can't see. So therefore they are very inefficient in terms of energy use, because the light that we get from them that we can use is only a tiny amount of the light that they actually emit. Okay, and then when we go to the sun, the entire visible spectrum is contained, is emitted quite strongly, and therefore the light from the sun appears to be more or less white. Right, so what's interesting about these results is the shape of the curve in each case is exactly the same. The only difference is a stretching of the axis. So if I take this curve from the heating element and I just stretch the x-axis by a factor of approximately 2, proportional to the temperature, then I will get this curve. And then if I stretch the same curve by a factor of 3, I will get this curve. Okay. So the shape of the curve is universal in some sense. All of these bodies show the same kind of curve for intensity as a function of frequency, and the only thing that they depend upon is wherever the maximum intensity is. Okay, and that is proportional to the temperature of the body. So there should be a good explanation for that. So this spectrum is known as the Blackbody radiation spectrum, or the Planck distribution. Later on it was named after Planck because Planck was the person who came up with the theoretical explanation for this curve. But clearly this should have a good explanation. No matter what the body is made of, it always shows the same light emission spectrum here once it's heated. Okay. So we should have a good explanation for that. And classical physics cannot provide a good explanation for that. So on this slide, I talk basically about what the classical physical theory tells you about this blackbody radiation. So here, because you probably haven't taken any thermodynamics class, you might not understand too much of this, and I will just briefly explain it. So if it's something you haven't seen before, then you'll just have to believe me that what I say is true. Later on, if you take the Yolmit Tonge Mulihak E class, so which is a class that I take in the 4th year, then I actually show this calculation, and then you'll be able to understand it in complete detail. Right, so to make it easier, I'm going to imagine that our light, which is being emitted, is contained in some side of some sort of conducting box here. And this is useful because that means at the edges of the box, the intensity of the light must go to 0 because the electric field intensity must go to 0. And that means that the light inside the box, because we know light is a wave, it can only exist at certain wavelengths, and it can only therefore exist at certain frequencies. So we have seen in the section on the Doppler effect, there is this relationship between frequency and wavelength. The speed of light must be equal to the wavelength times the frequency, and this means that the frequency must be equal to the speed of light divided by the wavelength. And here the wavelength is fixed. Okay, so lambda in the first case is here, in the second case it's here, in the third case it's here, and so on, right? So this is actually an example of quantization. You could say here that the wavelength is quantized because lambda can only take a certain set of values. Okay, so because the wavelength is quantized, it can only take on certain values, by this formula over here, the frequency is also quantized, and each possible value of the frequency is known as a mode of the system. Okay, and there's this theorem known as the equipartition theorem. This equipartition theorem is a theorem from classical thermodynamics. And what it says is that if you have a system which can emit energy in a number of different modes, then if you heat it up to a fixed temperature, each mode will have the same amount of energy. So in this case, it would mean that each of the possible wavelengths here would have the same energy and the same amplitude in the light. Okay. But this is a clear problem because the possible values of lambda are actually infinitely many. I can fit one wavelength in the box like this, or two wavelengths in the box like this, or 3 or 4 or 5, but the number of wavelengths I can fit in the box go up to infinity, right? And if I have infinitely many different modes, all with the same energy, then this predicts an infinite amount of total energy. Okay. which obviously is totally physically impossible. Okay, so the pictures here are one-dimensional. If you do the same thing in 3 dimensions, like we actually live in, then what you find is that the number of modes as a function of frequency are proportional to frequency squared, and this means that you will get an energy density proportional to frequency squared, and this is known as the Rayleigh-Jeans law, in the name of the people who derived it. But again, this law cannot be correct, because if you were to plot what that looks like on a graph, then energy as a function of frequency, you would get a graph that looks like this, and the total energy in the system is just the integral of this energy density, but this integral is clearly divergent, right? You get infinitely much energy out of this integral. So this was the problem with classical thermodynamics. It could not explain this blackbody radiation, the emission of light by a hot body. However, it's interesting to note that the Rayleigh-Jeans law, even though it's nonsense, it predicts infinite energy, it does actually get the start of the curve right. If you go back again to the plot we had on the previous slide of energy density as a function here of frequency, then for small values of frequency, the Rayleigh-Jeans law, which is plotted here, actually agrees pretty well with the observations. But at high frequencies, it runs into problems. So that means that something is reducing the energy density of these modes at high frequencies. Each mode at high frequency has much less energy than the Rayleigh-Jeans law would predict. Okay. So now we come to Planck's solution. So he came up with a method to reduce the energy of these high frequency modes, and his idea was to say that energy was quantized, so the total amount of energy you can have at a particular frequency must be given by a formula like this one here. Okay, so this means the energy, total energy of light at frequency nu must be equal to an integer, so here n is an integer, times some constant which was unknown, times the frequency itself, nu. Okay, so what that means is the larger nu is, the more spread out the possible values of energy are. So that's shown in the plot down here. So energy now is plotted horizontally, and depending upon the frequency nu 0, you get a certain amount of energies that are allowed. So here total energy is 0. Here this is 1h nu 0. Here this is 2h nu 0. Next one is 3h nu 0, and so on. Okay, and these are the only values of energy that light at this frequency is allowed to have. Okay, so note that n is an integer, so by considering the units of energy and frequency, we get that the units of h must be joule seconds. Right? Okay, so that will come in the next slide. Okay, so if you double the frequency of the mode, then that doubles nu in this formula, and that means that your possible values of energy get spaced out twice as far. And if you multiply the frequency of the mode by 3, then they're spaced out 3 times as far, like this. Okay. Now you can show, using the theory of statistical mechanics, that this means that as required, those high frequency modes contain less and less energy. Okay. So having a smaller set of possible energy values restricts the energy density of these high frequency modes. So this is very hard to explain. So I'm not going to try and explain it in this video, but it follows from the theory of statistical mechanics. And like I said, if you take the Joule-Mittongi-Mullihack and Joule-Mittongi-Mullihack E courses, you will see this explanation in detail. But anyway, this quantization of energy here solves the problem of the Rayleigh-Jeans law and the problem of infinite energy prediction. Okay, So Planck used the theory of statistical mechanics with his assumption about energy quantization to work out what the energy density should look like, and he came up with a formula that looks like this. So here U is energy density. Okay, and you can see it depends upon the speed of light, and it depends upon frequency, as it must do, and it depends upon here T is the temperature of the body, and it also depends upon this new constant which he invented to describe the quantization of energy of light. Okay, and it turns out if you take this formula here and you put it into this graph, then the shape of this graph depends upon the value of the constant h. Okay, so by fitting the theoretical prediction that Planck made to the experimental shape of this graph, you can calculate what the value of h must be. Okay, and you know, when you did that, you obtain this value. Okay, the value of h is very, very small, 6.63 times 10 to the minus 34 joules seconds. So yeah, it's a very small value, but with this value you can correctly predict the experimental observation of blackbody radiation. Okay, so this constant actually turned out later on not just to be important for light, but actually to be something fundamental about the universe. So it's very interesting that both of these constants, the speed of light and Planck's constant, are the same in this way. One of the big conclusions of special relativity is that the speed of light is not something special about light. It's something special about the whole universe and how space and time are joined together, right? And the same thing is true of Planck's constant. Although originally it appeared in a theory about light, it turns out to be something fundamental about the universe, and in particular fundamental to quantum theory. Okay. So before I finish this video, I just want to note, because this value is so small, if you take, say, visible light, so visible light has a frequency of about 10 to the 14 Hertz. So that means that one of these energy units that Planck predicted, which is h times the frequency, is about 10 to the minus 34 times 10 to the 14, which is about 10 to the minus 20 joules. Okay, so even though the possible values of energy are quantized, for visible light these units are so small together that ordinarily in a normal experiment you would never notice this, right? We can't possibly measure units of energy as low as 10 to the minus 20, or at least, you know, we couldn't at that time. So it's not surprising that we thought before that the energy from light was a continuum, that you could divide it into any energy value you like, whereas Planck's law says you can't, but the unit is so tiny that ordinarily you never notice the difference. Okay. Right, so that's the end of this video, which was on blackbody radiation, and in particular Planck's explanation for it in terms of the quantization of energy of light, which was the very first example of quantization in what became known as quantum theory.